could do this thing which is in structure, it's used, there are two matrices you're looking at. It's the P and the Q matrix. Q is the one we always look at it, is basically the proportion of each individual belonging to each of the clusters, yeah? And for different numbers of clusters. And then we have another matrix, which is the P matrix. This is just the allele frequencies of a SNP in one of the clusters. And you can see maybe that's kind of a problem, isn't it? Because say if I start, this is my cluster, then I can calculate the allele frequency for each of the SNPs. Simple, yeah? And then I can also say, okay, what is actually the ancestry of that? But then I think, oh, maybe this one got there, that changes the allele frequency and also the other matrix. So it's kind of an optimization problem. To find the best cluster, you have to calculate the allele frequency of each loci, and then you put individuals in a certain cluster, and then you think, this is not best. Maybe I'll swap some individuals around, yeah? And that's actually what this whole thing does. Just to let you know, the different ways to do cluster. Neighbor joining tree is a very simple one, very fast, very efficient. Yeah? And for our example, it works actually quite nicely. You see basically B and C a little bit closer to each other, and the other one are further apart. Yeah. Okay. Very quickly, maybe. This is a cool paper. I just found it last week. It's from Weng. We heard about him yesterday. He's a gun, certainly, in lots of fields. And he did develop his own thing, which is PopCluster, which came out 2022. And I asked around, anyone use PopCluster? I asked again. Cool. So even in that space, there's something. And he shows in his paper that one of the ones we use is SMMS. Who is using SNP? Oh, sorry, I can't say that. SNP. Yeah, quite a few. Okay, structure or admixture. Okay, and in this paper he shows basically his one is best and the other one are worse, and under different scenarios. And SMS actually came out last in most of the comparisons. This is sample size, yeah, and this is error, meaning if you're lower, you're better, yeah. And the same, if you have lots of populations, his came out the best, and SMS and SNP came out last. I say SNP from now on, okay? And why do we use SN SNP? Pardon? Exactly. He is good. He did also the comparison runtime, and SNP is by far the fastest. This is a log scale. It's 10 times faster than, almost 10 times than the next one, and so on. And structure is ridiculous, yeah? So we don't use it anymore, most cases. And he actually, it's very, the paper is very well to read because he also summarizes. Can you hear me? He summarizes all. Okay. The paper, and he says quite a lot of things. For example, he comes up with this really good idea. If you run a structure, you have to, on also fast structure, you have to make a choice, what kind of priors do I use? How much information I check in, yeah? And he shows those SMMS and also admixture and structure have problems if you have a really complex scenarios to converge and really depending on the prior. So he makes this kind of statement, and has actually a good solution how you could use some other methods to inform your priors better and more efficient. So he says basically do a simple cluster first instead of saying every, basically the easiest structure prior is you can be in any of the populations, yeah? So 1/k is your chance to be in a certain of them, yeah? And that's actually kind of the worst starting point you can have, yeah? And having a simple structure analysis and then put this as a prior in is much better. So that he came up with also some solutions for the other methods. So have a look at the paper. It's worth a read. Okay, very quickly I tried it. So what is actually structure and is doing, yeah, and also fast structure admixture is the same thing. It's just the likelihood solve is different and more efficient. SNMS is different. It's a non-model-based method. It optimizes without much ecological, genetical knowledge. Yeah? Except maybe Bill will tell me there's a paper that kind of proves it's linked to coalescent. I'm not sure. So what it does actually, you start, say, with these two matrices. The first one is your SNPs and your populations, and you calculate the allele frequency for each of the SNPs and put that in this matrix called the P matrix. The Q matrix is you do basically for every of the individuals you have, you give them a proportion what you think in which of the group they are, yeah? And a prior normally even is 1 over K would be in here, yeah? And then in the version of non-admixture, yeah, we only allow an individual to be in one of that one. So there would be only 0 and 1s in here. So we say this individual number, whatever, 3 is here. Then we check out basically matrix of if you're, because this is K, or if you're in this population, what is my allele frequency of a certain loci, yeah? And then I can use Hardy-Weinberg and say, okay, the chances that this individual with this kind of ancestry in this, at this loci has a certain likelihood to occur, yeah? And you can do that for all of the loci and for all of the individuals, and then you get a global kind of likelihood of your whole setup in this state. And then obviously you can hopefully see, I jiggle a little bit one of the matrices and then optimize that and try to find a pattern that has a nice thing. And here you can see maybe the advantage of structure. It uses actually here Hardy-Weinberg. Very important, Hardy-Weinberg is meant to be in one of your clusters to hold, not between clusters, only within the cluster. So it uses a genetic principle, yeah? SNMF doesn't do that, yeah? It's something is beyond my pay grade, sparse, non-negative matrix factorization. I don't know what it does. It somehow optimizes these matrices as well, but without any kind of genetic model behind it, okay? And in the non-admixture version, you can basically say, oh no, you're not in a single population from the beginning, and then you get something like a weighted average. You still can calculate likelihood, it's just more computation, yeah? Okay, and that's basically the algorithm that's used. Repeat, change, calculate P, calculate Q, and wiggle it a little bit and optimize it until you found a good solution. And structure is using a Bayesian approach, admixture is using a maximum likelihood approach, it's faster. Fast structure, you use something like it's called EM. I have no clue what it is, it's very efficient and very fast, yeah? And then we get these beautiful structure plots. And now I have to check what's my time. Yeah, okay. Almost finished. Give me another, is that okay? 5 minutes, and then probably Bill will go over 5 minutes. Okay, very quick. This was my situation. I just want to show what it is. You could have done a PCOA or PCA. That's the structure for my simulation. Look at this in the center. It's this kind of which were close to each other, yeah? What would structure do? And there's a nice implementation in Dart. If you want a structure and you have a computer, you can spare for a week. Nothing stops you to run it, yeah? We have also some code to parallelize the whole thing. So if you run it, you get these beautiful things, and I won't go over there, but basically the Ivano plot says the likelihood, and you go to the one which is to avoid overfitting, where this levels off, yeah? Or you do some differentiation and then you use the one where we have a maximum. So in this case, K equals 4 is probably a good one, yeah? And we know there were 5 populations, 2 were close to each other. So if I run structure with no admixture, that's important, I get this beautiful plot. 4 populations, separate B and C is the same thing. It's not a wrong answer, you know, because they're really close to each other. And we have a beautiful function, I have to say that you can spatially plot your results on a map in Dart, I think. think it's just cool, it doesn't help much, but that's how it is. Okay, I don't go over that. When you run structure, you have to have more than one run on a certain K, and most people don't look at that. We have a nice function to plot that, and you can see some of the Ks, even the no admixture models have some funky different results, yeah? They're not all the same, and that could give you already a hint there's something else going on, okay? Then we run structure with the admixture mode. Be aware it's no admix equals false. Whoever come up with this is a comparison of the two. And then the admixture model looks like this, just to make it sure. Both of them are true in some sense. This tells me there are 4 populations. This tells me, yeah, there are 4 populations. Both of them have k equals 4 as maximum, but there seems to be something going on in B and C, and it's not wrong, because I simulated that. But be aware what, if you don't know that, which one do you run? Both to see that? Probably would be a good idea, but do we actually do that? Maybe not. One final thing and then stop. This is also from Jonathan, and I think it's one of the best visualization what I tried to say at the beginning. When you find someone is in the same cluster, what does it actually mean? It means basically you have common ancestors back in time, yeah, and therefore you are in the same cluster. But it has all this kind of history compact into that. And there could have been, he didn't do that, someone coming over. You still have the majority of your background is from there. Yeah? So what you see in the end is not really gene flow or something. It is more this compressed history in boxes. That's really important when you do this kind of runs. You can do run fast structure, and that's the last thing I want to show. That's structure with admixture and no admixture. Fast structure, if you don't know, has not this no admixture version. It has just different priors. Means here simple says everyone is kind of likely to be in everyone, is this 1 over k scenario more or less. And logistic is a bit more, allows for more complex scenarios. I'm not sure, that's what they all say, what it means. Good news in some senses, the simple one is more close to that, but you can see they're all slightly different, and depending on your runs, you may have different interpretations. And nothing of this is false in some sense, it's just a different way how you represent the history that has happened.